We're happy to have Mr. Ian Banta from University of California, Santa Barbara, telling us about non-decoupling new particles. Please begin.
First, I'd just like to say thank you to the organizers for inviting me to give this talk, and thank you to the audience for listening. You should feel free to interrupt with questions during the talk if you have them, or I'm happy to answer questions at the end. All right, so I'll be talking to you today about non-decoupling new particles, and this is based on work completed in collaboration with Nathaniel Craig, Tim Cohen, Xiaochuan Liu, and Dave Sutherland. So I'll start things off with a question one might wonder. Have we discovered all particles which get most of their mass from the Higgs? All the fundamental particles in the standard model, if they're not massless, get mass from the Higgs, but that's not a requirement for new beyond the standard model particles. You could wonder, are they going to be like the standard model particles and get their mass from the Higgs, or gain it through an explicit mass term? And these particles will be the focus of this talk, and we, in our work, have given them the name of Loryons. So the next question you might ask after this, have we discovered all particles which get most of their mass from the Higgs, is why do we care? Why is that an interesting class of particles to pick out and wonder whether we've discovered them? There are a few reasons for this. One is from the point of view of effective field theory analysis of the standard model. So it is likely, looking at the historical record, that the discovery of new beyond the standard model physics will be seen first, not through some direct search that directs the particle or detects the particle directly, but rather through observing the indirect effects of new physics on standard model interactions. A principled and consistent way to do this rigorously is with effective field theory, but the presence of a Loryon would affect the effective field theory analysis that you can carry out. So most commonly, currently effective field theory analysis of the standard model is done in terms of SMEFT, or the standard model effective field theory. And this is written in terms of the Higgs doublet, H, and it linearly realizes the electroweak symmetry SU2L cross U1Y. If, however, you're trying to integrate out a Loryon and describe the effects of such a particle using effective field theory, you can't do so using SMEFT. And you instead need to use heft, or the Higgs effective field theory, which is written in terms of the physical Higgs boson H, and it linearly realizes only the U1 of electromagnetism and non-linearly realizes the full electroweak symmetry. And this has been noted back as far as 2016 and has been the subject of some work. So effective field theory analysis is one reason, if you want to be sure you're not missing something and you're doing your analysis properly and looking for BSM physics, knowing either that you might have a Loryon or that you can rule out the possibility of Loryons would have a significant effect there. Second, Loryons, by definition, in order to get most of their mass from the Higgs, could have a significant effect on the Higgs effective potential, and thereby on the electroweak phase transition, potentially making it strongly first order. And this is of interest both from the point of view of electroweak baryogenesis and trying to explain the matter-antimatter asymmetry, or if you're interested in gravitational wave physics and the possibility of a stochastic gravitational wave background, that could arise from a strongly first order electroweak phase transition. And this is an extension of this work that has come out within the past week or two. Third, Loryons don't have an arbitrarily large search space. Generally, if you introduce a new BSM particle and you make it particularly heavy, it will decouple and will have a vanishingly small effect on standard model interactions. But for Loryons, in order to maintain this criteria that they get most of their mass from the Higgs, if you increase the mass of a Loryon, you have to increase its coupling to the Higgs at the same time. This means that Loryons are by construction non-decoupling. They'll always have a significant effect because if you were to try to increase the mass too much, your coupling to the Higgs would become too large and would violate unitarity. And so if you want to have a theory which obeys unitarity, your Loryons can only be so massive. There is some, and this upper bound to the mass means that there's a finite search space. And so you could imagine, in principle, this question I proposed at the beginning, have we discovered all particles which get most of their mass from the Higgs, could receive a definitive answer of no, or a definitive answer of yes. We have discovered all such particles. There are no more, and we know this because of unitarity. There simply can't be such particles with larger masses. So with that as a sort of motivation for why Loryons are an interesting class of particles to look at, I'm going to give you, the last thing I wanted to say about why Loryons are an interesting class to look at is because, again, since they're required to have a strong coupling to the Higgs in order to get most of their mass from the Higgs Vev, there's good discovery prospects in the near future from colliders and the like and signals, distinctive signals you would see from Loryons at colliders. And so this goes along with having a finite search space. As you imagine, if there are Loryons, we're likely to see them soon. And if there aren't Loryons, we could determine that certainly. Okay, so now with that motivation, I'll give you a roadmap for the talk and where I'm going to go in our study of Loryons. So first, I'll tell you about some assumptions we made and what Loryons we considered in our work and how and why you might want to relax these and what effect they have. I'll set up notation for the rest of the paper to make sure we're all on the same page. Then I'll sharpen up this criteria for when you're required to use heft. So far, I've said this sort of vague, the particles need to get most of their mass from the Higgs and their coupling to that. I'll sharpen that up and tell you when precisely you must use heft as your effective field theory description. I'll talk a bit more precisely about this upper bound on the mass that you can get from unitarity and how we go about converting that from a general idea that the coupling can't be too large to a sharp upper bound. Then I'll tell you about experimental constraints on Loryons. Because of this upper bound from unitarity, they will have to be near the Electroweak scale, and there are significant experimental constraints on them. But as you might expect from the fact that we've written a paper here and I'm giving this talk, there is still the possibility for Loryons, and there's regions of viable parameter space. And then finally, I'll tell you some future directions and make some concluding remarks. So are there any questions about this setup before I dive into the first bullet point?
One short question, but you might answer it in the definitions. Do you consider neutrinos to be Loryons?
So we don't make any specific statements about neutrinos, and we're interested in beyond the standard model particles rather than standard model particles. In general, we'll also be interested in massive particles near the Electroweak scale, because we're interested in integrating out such particles and describing them with effective field theory. And so you'll want them to be at least somewhat heavier than the energy scales of the processes you're considering.
See, so you are focusing on particles which are hundreds of GeV, and you are not considering particles which are relatively light but feebly coupled.
Yes.
I see. Thank you.
All right, then I'll get into the assumptions we made and the restrictions we placed on the BSM Loryons we consider. So the first is that we consider scalars and vector-like fermions, and we don't consider chiral fermions or new vectors. We require that there be no new custodial symmetry violation to the one loop level. This means that all of the fields we consider can be written as a representation of the custodial symmetry of the standard model, the SU2L cross SU2R custodial symmetry. We will impose a Z2 symmetry on our BSM Loryons, which is often weakly broken to allow them to decay, and will require that all new charged particles promptly decay. For many of these, for these assumptions in general, you could relax them. And what happens generally if you relax them is that there are additional experimental constraints that you'll have to worry about. So for example, if you were to not require that your new charged particles promptly decay, you'd have to consider limits on heavy stable charged particles. You could allow for custodial symmetry violation, then you'd have to check that you don't violate the experimental constraints on that, and so on. We impose all of these for calculational simplicity, and also because they give you the sort of characteristic or irreducible effects of Loryons, what you get as a result merely of a Loryon being a Loryon, without worrying about other constraints that come in from the particular representation you're choosing. But in principle, you could relax these assumptions and have a broader parameter space to consider. One I'll highlight in particular is this assumption or imposition of a Z2 symmetry on the BSM Loryons. This means that they will contribute at loop level, but there will not be tree level effects from the new Loryons. This is a particularly significant restriction, and many people have examined cases of, say, a new singlet, which is coupled to the Higgs and does have tree level effects. These are Loryons, and you could consider them. Again, we make this assumption because it gives you the necessary effects you get from having a Loryon. Any Loryon will have loop level contributions to the standard model interactions, but it won't necessarily have tree level contribution. So by making this assumption, we're looking at minimal examples of Loryons that do the smallest amount. Yes, one, I see your hand raised.
So in your setup, you strictly stay in the standard model gauge group.
Yes.
Except for this G2 symmetry you impose.
Yes.
Okay, good. Thank you.
Mm-hmm. And these are, again, you could design more complicated models which have additional gauge groups and beyond the standard model, or with chiral fermions. All of these things are possible, and you could still have Loryons if such particles receive most of their mass from the coupling to the Higgs. But these are additional complications beyond what is necessary for a particle to be a Loryon. Okay, so with that, we have to set up some notation. For example, if you have a scalar phi in the custodial representation LRY, so this is the charge, the representation under the SU2L vector, which is gauged, the SU2R piece of custodial symmetry, and then the hypercharge U1Y, where this Y is the hypercharge of the field on top of any hypercharge it receives from its representation R, where we consider hypercharge as is usual to be the gauging of the T3R generator of SU2R. So for example, a neutral singlet would be custodial representation 110. A charged singlet would be custodial representation 1,1 An electroweak doublet, like the Higgs, for example, with hypercharge 1/2, would, in our notation, be the custodial representation 2,2 Since the hypercharge 1/2 of the Higgs doublet comes from its representation as a doublet under SU2R, there's no additional hypercharge on top of that. So that's the notation we've used. So for such a scalar in this custodial representation, there are 3 terms of most importance that you can write down in the Lagrangian. on the first line here is a mass term for the new field phi. So this mx squared parameter is the explicit mass of the new field. It's the mass it gets just from having a mass term. And this rho parameter in the denominator is 1 if the field is real and 0 if it's complex, such that mx squared is the mass of the particle in the absence of interactions with the Higgs. Second, you can write down a Higgs portal interaction, and that's the second line here, where you have the new field squared and your Higgs doublet squared. This has a quartic coupling, which we've called lambda h phi. And from the structure here, you can see that all the components of the new field phi will acquire the same mass as a result of this interaction after the Higgs acquires a VEV. That is, this Higgs portal interaction couples all the components of our new scalar phi to the Higgs in the same way. But you can also write down a second type of cross-quartic interaction where the SU2 contractions take place through copies of the generators of SU2L and SU2R. And this term, which we've given cross-quartic coupling lambda h phi, will generally give different contributions to the different components of phi after the Higgs acquires a VEV. And in general, then you get a mass spectrum, which looks like so, where each particle acquires some contribution from the explicit mass squared, some contribution from this first cross-quartic coupling to the Higgs, and some contribution from the second cross-quartic coupling, which varies depending on which component you're talking about. Here, the specifics of what happens is that after the Higgs acquires a VEV, it breaks the SU2L cross SU2R of custodial symmetry down to an SU2V, which is now preserved in the presence of the VEV. And our scalar phi will split up into different irreducible representations of that unbroken SU2V. And those representations that are present depend on the representations of the original custodial symmetry, and this contribution from the second cross-quartic depends on which components you're talking about. Whichever it is, we can collect all of this dependence on the Higgs VEV into some effective quartic coupling lambda v. And so we have the mass squared of our scalar, of the components of our scalar phi as the sum of two terms, an explicit mass, mx squared, and a Higgs VEV dependent mass, written here as 1/2 lambda v times the Higgs VEV v squared. For a pair of vector-like fermions, the situation is similar. So as they are vector-like fermions, you can write down a vector-like mass. And additionally, you can write down a Yukawa coupling between the Higgs and a pair of new fermions. Unlike with the scalar, we need fermions in two different custodial representations because the Yukawa interaction only includes one copy of the Higgs doublet, whereas the cross-quartic couplings for a scalar included two copies of the Higgs doublet. So in order for this Yukawa interaction to be a gauge singlet, you need two vector-like fermions whose representations under SU2L and SU2R differ by one from each other. And that's that condition again is just necessary for this Yukawa interaction to be a gauge singlet. The two vector-like fermions could in general have different vector-like masses. This doesn't have a significant qualitative impact on the phenomenology, so we set them equal to each other and check that this does not have a significant impact. Similarly to the scalars, these vector-like fermions will have some mass spectrum where the different components of your fermions get contributions to their mass from two sources, either this explicit vector-like mass, which does not depend on the Higgs VEV, and a contribution from the Yukawa interaction, which does depend on the Higgs VEV. unlike the scalars, where we had two separate cross-quartic interactions, one which gave the same mass to every component, and a second which introduced some mass splitting, since we have two different representations here, we generally can't avoid having mass splitting. The one Yukawa interaction we write down gives different contributions to different components of our fermion multiplets. I haven't written down the explicit formula here because it is simply a particular combinatoric and group theoretic factor, again, based on decomposing into irreducible representations of the unbroken SU to V after the Higgs field acquires a VEV. The salient points to notice are simply that some components don't participate in the Yukawa interaction, and they only get the explicit mass. But other components do, and they receive a contribution, which we can write in terms of some effective Yukawa coupling Y sub V, which again can be related to Y1, 2 through some group theoretic factors. And these components which do acquire mass are paired up. One of them, its mass becomes larger, and the other, its mass becomes smaller as you turn on this Yukawa interaction. Yes, Thomas, I see you have a hand raised.
Yeah, you said you checked that there is no strong impact if you choose the two masses equal, but if I, for example, would choose one mass to be basically zero and the other mass relatively large, I'd naively expect that I would get one fermionic state which is relatively light and one which is pretty heavy in this setup.
So it
and
generally
one is nearly decoupling, and the other one could be somewhere in the around the Electroweak scale, maybe.
Right. So that generally does not happen because these components which do participate in the interaction with the Higgs, generally the mass eigenstates are some linear combination of the components of psi1 and psi2. And so here where we have a factor of mx, if you were to allow, and for an mx1 and an mx2 which differ from each other, you wouldn't get some components which have an mx1 and others which have an mx2. They would generally have some linear combination of mx1 and mx2 with order 1 coefficients. It is the case that for the components which don't participate in the Yukawa interaction, they could have, if you were to take one of your explicit masses to be very small, you could get some components which are relatively light, but these would be components which don't couple to the Higgs at all and don't participate in those interactions. The degrees of freedom that do couple to the Higgs are generally, the mass eigenstates are linear combinations of your two representations, and therefore they mix the two explicit masses if you were to keep them separate.
So this would be a light state then, which is, however, not getting its majority of the mass from the Higgs, you're saying.
Right, and not the majority, but it is not coupled to the Higgs at all.
Okay. Okay. Thanks.
Yeah, and this is tied up somewhat in this determination of the particular form for the YVs. So if you would like to see more of the details of how those linear combinations form, I would encourage you to go look at our paper. Great. So now we have these particles, these scalars, and these fermions. And we want to now sharpen up this criterion for when are these particles getting most of their mass from the Higgs, and when do you satisfy the claim I've made that they must be analyzed using hep. So the first step is if we take a scalar phi, we can integrate it out using functional methods to all orders in the Higgs doublet H and to 2 derivative order. And if you do this, your effective Lagrangian includes the terms I've written out here. And the important thing to note about the form of these terms is that they depend on this mv squared of h, which is the Higgs dependent mass of the Loryons. You can see if you set the Higgs doublet to its VEV, this mv squared of h is just the physical mass of the particles. And that this mv squared of h factor appears in the denominator of certain terms. Here we have a log mu squared over mv squared of h. And here we have a log, or not a, in this non-log term, we just have the lambda v squared over 6 mv squared of h. And so we get this Higgs dependent mass in the denominator. Now this is to all orders in h. If you're going to analyze this using SMEFT and write it in terms of SMEFT, you want to write this as polynomials as in terms of powers of the Higgs doublet h. And so to do so, you can expand these 1 over mv squared of h terms in the quantity lambda v h squared over m explicit squared. If you make an expansion in this parameter, then you get an infinite tower of operators with increasing powers of the Higgs doublet, and this matches the form of SMEFT. But your expansion in that quantity will converge at the VEV, the physical VEV of the Higgs, only if lambda v squared over 2 is smaller than the explicit mass squared. Otherwise, your expansion parameter is greater than 1, and these higher powers of the Higgs doublet contribute more and more significantly. You have an infinite tower of operators whose effects become more and more important as you go further up the tower. And this is no good if you're looking to do an EFT analysis. What you want to do if you're trying to compute with SMEFT is have this infinite tower, but have them become less and less important as you go up the tower, such that you can truncate to some finite order and compute from there. And this will only happen if this expansion parameter is less than 1. Otherwise, your SMEFT expansion does not converge at the physical vacuum. For heft, as I said, it's an expansion in the physical Higgs boson little h, and that is around the VEV of the Higgs. And so to write this in terms of heft, you expand not in powers of the Higgs doublet, but you write the Higgs doublet in terms of the VEV plus the physical degree of freedom h. And you expand in powers of little h rather than in terms of big H. And by definition, since you're expanding about the VEV, you won't have any problems with convergence of your series. And so this is the source of why you cannot use SMEFT if the particle is too strongly coupled to the Higgs and receives too much of its mass from the Higgs. The expansion you write for SMEFT will not converge at the physical vacuum. Okay, so now that we've seen that, it's useful to make a slight change in parameters, that we can define this quantity f sub v to be the contribution a particle gets to its mass from the Higgs VEV divided by the total mass squared of the particle, such that Fv will be the fraction of its mass squared this component of the new scalar field gets from the Higgs VEV. And our criterion for heft being necessary is then that if any one of these components receives more than half of its mass squared from the Higgs, your SMEFT expansion will not converge. And so that's just saying the max over all of the components of this Fv, which we define as F max. If that is greater than or equal to a half, then you must use heft as your effective field theory description. For fermions, the story is similar. I haven't written out the full form of the effective Lagrangian here because it is slightly more complicated than the scalar case, but the end result is exactly the same. For the fermions, the relevant F max is the fraction of its mass rather than its mass squared that the particle gets from the Higgs. And it is again, if the Higgs dependent contribution is more than a half of the total mass for any one of the particles, then you are required to use heft because a SMEFT expansion does not converge at the physical vacuum. Are there any questions about that before I move on to the next topic?
I have one question concerning your initial Lagrangian. So in this Lagrangian, you are assuming that the Higgs, the scalar, and the vector-like fermions are elementary, and you don't have any higher order representations, and it's linear realization of the SU2L cross SU2R. Is this correct?
Yes, this is correct. So for the EFT Lagrangian, after you integrate out, that will, if you're using heft, only linearly realize the U1 of electromagnetism. But our UV Lagrangian, which has our Loryons as degrees of freedom, it linearly realizes SU2 cross U1, yes, as well as SU3. These Loryons could be colored if you like, but all of those are linearly realized in our UV Lagrangian.
I see. So this is, but this is assuming that all particles here are elementary. So
Yes.
if you would have nonlinear realizations of the SU2L cross SU2R or some components, then that would be a possible extension or generalization.
Yes, and yes, and I would categorize that, I would say, under the general category of we've made the assumption that all of our new Loryons are in representations of the custodial symmetry of the standard model. And we've done that because custodial symmetry violations are well constrained. You could relax that and have more complicated models, but we have not done so here.
Okay, thank you.
Yes. Okay, so the second of the criteria I mentioned earlier that I will sharpen up a bit for you is unitarity, in that we said, well, if you increase the mass of these particles, you must increase their coupling to the Higgs at the same time to maintain this condition of Loryons, and eventually you run into problems with unitarity. So to make that a bit more precise, we're talking about unitarity of the S matrix, that we want our theory to be unitary, and that's expressed in terms of the S matrix. And you can massage this to transform it into a condition on T, the transfer matrix. And loosely, you can see that this condition on T is saying that, well, the imaginary part of your amplitudes can't be, I need to scale as your amplitude squared. And so you can't make the amplitudes themselves too large or you will violate this condition. To be a bit more precise, what one can do is perform partial wave decomposition of your amplitudes. And this translates the above bound on the transfer matrix T into a constraint on the partial wave coefficients, that the real part of each of the partial wave coefficients must be less than a half. And this is something you may be most familiar with in the context of taking the high energy limit. This is a useful thing to do if, for example, you have a contact interaction, like this cross-quartic term we have for the Loryons, which is constant with energy. And so in the high energy limit, you can simply obtain a bound on how large that contact interaction is allowed to be. Or in other contexts, if you have some amplitude that grows with energy, such as longitudinal scattering of the Electroweak vector bosons in the standard model without incorporating the Higgs, you have an amplitude which grows with energy, and you can use such a partial wave analysis to find an energy scale at which new physics, which in this case was the Higgs boson, had to enter to maintain unitarity. But here, I want to emphasize that you can consider this bound not just in the high energy limit. Our theory needs to be unitary, not just at large center of mass energies, but at all center of mass energies at which you can scatter the particles off each other. And so what I've given you here is a formula for the 0th partial wave coefficient. This is the one we'll consider in order to obtain a bound you can look at higher order partial wave coefficients as well. They give weaker bounds. And so this is found primarily by integrating your amplitude to go from some initial state I and elastically scatter to some final state F, with respect integrating it over the angular variables, gives you the S wave coefficient. And then we have this prefactor out front, depending on the momenta of your initial and final states and the center of mass energy, which properly implements the bound in when considering it all center of mass energies rather than just the high energy limit. And this, again, this partial wave unitarity bound will give us a bound on the size of the amplitude by imposing that this A0 not be greater than 1/2 in magnitude. Now, this, considering it at all energies, at all center of mass energies, is particularly important because it turns out that the dominant contribution to the bound comes not in the high energy limit, but close to threshold, where your amplitude is dominated by T-channel exchange of a Higgs. So what I'm showing you here in these plots are, we're considering scattering where our possible initial and final states are 2 Loryons or 2 Higgs bosons. These examples are for our new Loryon being a gauge singlet scalar. So the red curve and the blue curve are the eigenvalues of a 2x2 matrix of partial wave coefficients. And it is these eigenvalues that must be less than 1/2. And I'm showing you 2 examples. One, on the left, we've set the mass of our new singlet scalar equal to 500 GeV. It receives all of its mass from the Higgs and it's coupling to the Higgs. And the self-coupling of our new Loryon is small relative to some value, which I'll talk about in a moment. And what happens here, you can see, is that in the high energy limit, you asymptotically approach values that are 0.1 or smaller or so in magnitude, but close to threshold for root S smaller, we get this spike that is due to T-channel exchange of a Higgs and 2 Loryons elastically scattering via that exchange. This is affected by the self-coupling of the Loryons, and so if you turn up this self-coupling, you can get a slightly higher upper bound on the mass of your new Loryons. And so that's the example I'm showing you here, where now this red curve is asymptotically approaching 0.5 in the high energy limit, and that's due to this contact interaction between the Loryons. But close to threshold, the dominant interaction is not, for elastic scattering of 2 Loryons, is not the contact interaction, but T-channel exchange of a Higgs. And so this T-channel exchange generally gives you an upper bound on the mass from unitarity that is of order several hundred GeV. And this is a factor of a few stronger than the bound you would get if you just considered the high energy limit and bounding this coupling based on the amplitude of 2 Loryons scattering to 2 Higgses or the like. Okay, so that is what I have to say about unitarity. So there are no questions on it for the moment. I will go ahead and get into the experimental constraints on new Loryons and whether they're experimentally viable. So the constraints we consider first are constraints from Higgs couplings. Because of the Z2 symmetry that we've imposed on our new Loryons, the standard model interactions in which we will see the strongest signal are those which arise at loop level rather than at tree level. Our Loryons don't make any tree level contributions, so the effects which have standard model tree level contributions don't get a significant correction from Loryons. But those which only arise at loop level in the standard model, such as Higgs to gamma gamma or Higgs to glue glue can and often do receive significant corrections from new Loryons. For Higgs to gamma gamma, for example, this arises through a loop of charged particles. If you introduce new charged Loryons, they can run in the loop. And similarly for HGG with new colored particles. We also consider Higgs decays. If you have a new particle of less than half the Higgs mass, it can contribute to the Higgs decay. And our numbers for these come from recent publications by Atlas and CMS. We also consider precision electroweak measurements. Because we've imposed that our Loryons are in representations of custodial symmetry, considering precision electroweak measurements amounts to considering the S parameter. And this receives contributions whenever you have a custodial multiplet, which has some mass splitting between its components. And so considering these precision electroweak measurements amounts to placing a bound on the amount of mass splitting we're allowed to have. Finally, we also consider direct searches for these new particles. This comes from various sources because it depends very strongly on the particular representation you're considering. Right, so with that, I will go ahead and show you some plots for various examples of Loryons. So these are running in order along the top row, left to right. We have a neutral singlet scalar. We have a charged singlet scalar with charge 1. We have an electroweak doublet with hypercharge 1/2, so an inert Higgs doublet. We have an electroweak triplet with hypercharge 0. And then the last two are in the fundamental representation of SU3. So these are colored scalars. They are electroweak singlets with charge either -1/3 or +2/3. All of these plots are plotted on two axes: the mass, the physical mass of the new particle, and the fraction of that mass it receives from its coupling to the Higgs. The blue region with a solid boundary is ruled out by unitarity constraints. As promised, it varies from about 500 to about 800 GeV, depending on the fraction of mass from the Higgs. The purple region with a dot dash boundary is the limit from direct searches. The green region with a dashed boundary is constraints from Higgs decay, and the orange region with a dotted boundary is from Higgs to gamma gamma and Higgs to glue glue. So the main 0th order takeaway I would want you to get from these plots is that there is a very significant white region. Generally, these constraints from unitarity places an upper bound and direct searches place a lower bound, but there's plenty of room in between. And the Higgs couplings are controlled primarily the level a particle contributes, as long as it's significantly above the Higgs mass, depends on this F max parameter. And that leaves plenty of viable region for these particles. So Loryons are currently at least alive and well and could be discovered. One thing you might notice looking at these plots is that for our 3 electroweak representations, which introduce charged particles, this orange curve looks very similar for all 3 of those. That is no accident. It's in fact exactly the same for all 3 of them. And the reason is that all 3 of these representations introduce exactly one charged particle, which has charge 1. Any other new components of the multiplet are neutral. And so this is the bound from H gamma gamma on having a single new charged particle. The reason I've picked these representations in particular to show you is because it turns out that you can only have a single charge particle added, getting more than half of its mass from its coupling to the Higgs. If you were to try to add more, say from some larger representation or by increasing the hypercharge, that would be ruled out. It makes too large a contribution to H gamma gamma. Similarly, this is also a problem for our new vector-like fermions. A single new vector-like fermion that is charged contributes 4 times as much as a new scalar. And this is enough that it makes too large a contribution to H gamma gamma. So those would not be consistent with the measurements, except for one loophole, which I will address now. And this loophole is that in the standard model, as I said, any charged particles can run in the loop, connecting the Higgs to 2 photons. In the standard model, that includes primarily the W bosons and the top quark, since the other fermions are only weakly coupled to the Higgs. And it turns out that vector bosons contribute with opposite sign to this amplitude as compared to scalars and fermions. And in the standard model, the contribution is dominated by the W bosons. But if we were to add lots of charged BSM fermions and or scalars, which are coupled to the Higgs, we can flip this scenario around and make it so that the scalars and fermions dominate the contribution. And if you add just the right amount, you will in fact match the magnitude predicted in the standard model for the Higgs to 2 photon coupling, while simply having flipped the sign because now the scalars and fermions dominate rather than the vector bosons. And this plot is illustrating that. So here the blue and the green regions are ruled out by ATLAS or CMS. The white region is the allowed band at the 2 sigma level for the Higgs to 2 photon coupling. You can see that it's on the x-axis is a measure of how much new stuff you've added. And initially, if you add some, it very quickly exits the viable region. The actual value on the x-axis at which it crosses is about 1. But if you were to add enough new particles, you would flip this and you re-enter the viable region. In this measure, it depends on the charge of the particles, the fraction of their mass they receive from the Higgs, and this eta is indexing whether your particle is a scalar, for which it's 1, or a vector-like fermion, for which you get a factor of 4. And so if you were to add, say, 40 charged singlets, receiving all of their mass from the Higgs, or 10 charged Dirac fermions of charge 1, receiving all their mass from the Higgs, you would achieve this effect and re-enter this viable window. All right, so with that, the fermions do become somewhat viable then, and you can think about which fermions could you add which satisfy the other constraints. And so here I've just given you a couple of examples. These are in fact the 2 examples that are not ruled out still. So on these plots, the blue region with a solid boundary is once again showing you the unitarity bound. The green region with a dashed boundary is showing you the bound from the Electroweak precision parameter S. You may or may not recall, as I said earlier, that for the fermions, the Yukawa interaction necessarily introduces some mass splitting. Well, for the scalars, you can give the same mass to all your components. For the fermions, you unavoidably get some mass splitting. So that's why this Electroweak precision bound must be there. And the orange region with a dotted boundary comes from direct searches. Here we're using the LEP bound on the existence of charged fermions, as well, which gives a lower bound for the mass, as well as a reinterpretation of Electroweakino searches via where the components of your multiplet decay down via emission of W and Z bosons, which you can then detect. So that is the reason for this orange region. And it is the same constraint of the Electroweakino search. It just gets stretched and contorted and remapped in order to fit with the mass spectrum that you get for these particular representations. So again, you can see there are some white regions, much more for this model, which has a electroweak doublet fermion coupled to a pair of electroweak singlets. Then for this model, which introduces either a set of 3 singlets or a set of 3 singlet fermions whose charges differ in integer steps. So we have charge -1, 0, and +1, as well as a doublet of fermions. This is much more strongly constrained, and the larger fermionic representations are ruled out by these direct search or electroweak precision constraints. For the scalars, I haven't shown you any updated results due to this loophole flipping the sign of Higgs to gamma gamma, because it's the same type of story as you had for these plots. There's some unitarity bound, some direct search bound, and there's a viable region in between, as long as you make sure to properly hit your viable window for Higgs to gamma gamma. Okay, so that's the state of the current experimental constraints. We could ask, what could further close this parameter space and eventually rule out Loryons? If you're a pessimist, if you prefer to be an optimist, you could ask, well, what can we do that could lead to a discovery of Loryons? So one possible thing to look at is Higgs wave function renormalization. This is currently subdominant as compared to the unitarity bound, but any new particles which couple to the Higgs will affect the Higgs wave function renormalization, and a precision measurement of it, such as at a future lepton collider, could produce a competitive bound and an experimental constraint on BSM Loryons. Second, well, new or improved direct searches, and this depends heavily on the particular representation you're considering. So we list some possibilities in our paper. And third, well, if you were to just improve the precision of the Higgs coupling measurements, this would rule out more of the parameter space. So one is if Higgs to gamma gamma or Higgs to glue glue, if they're measured more precisely, you squeeze closer to the standard model values, and these constraints will take up more of the parameter space. But additionally, there are 2 new signals you could measure, which, if measured with sufficient precision, would provide qualitatively new bounds on the parameter space. So the first of these is Higgs to Z gamma. This is relevant mostly for this possibility of flipping the sign of Higgs to gamma gamma. You may have wondered when I was discussing that effect, well, is there anything that's sensitive to the sign of Higgs to gamma gamma? It would tell us whether we have the standard model value or some other. And the best tool for doing that is this Higgs coupling to a Z boson and a photon. Because any particles which contribute to Higgs to gamma gamma generally also have a non-zero coupling to the Z boson, so contribute to this interaction, but they contribute with a different magnitude, and thus, while you'll have precisely matched the standard model value of Higgs to gamma gamma, you won't have matched the standard model value of Higgs to Z gamma in general. You can cook up models which, because of cancellations, do indeed match it, but it would be a significant reduction in the possible models which are viable by flipping Higgs to gamma gamma. The second measurement, which would be of particular use to Loryons, is a measurement of the Higgs cubic self-interaction. Because these particles are by definition strongly coupled to the Higgs, they will have a significant effect on the Higgs cubic. And so a precision measurement of the Higgs cubic would provide a constraint on Loryons. So in particular, I can show you what these updated constraints would look like for projections for the HL-LHC. So here, the blue region with a solid boundary is once again unitarity, and purple region with a dot dash is direct searches, which we haven't updated with any projections. These are the same as the current bounds. The orange region with a dotted boundary is Higgs to gamma gamma constraints. So you can see it for current constraints, it lives up near F max equal to 1. With the HL-LHC projections, it moves down significantly to F max of around 0.7. And this green region with the dashed boundary is the constraint from the Higgs cubic self-coupling at its projected sensitivity. And you can see this comes in at a qualitatively new direction as compared to Higgs gamma gamma. It in fact roughly parallels the unitarity bound and comes in from the right rather than coming down from the top. And for the projected HLLHC measurement, it's about the same as the unitarity bound. So currently it doesn't give us anything extra as compared to the constraint from unitarity, but that unitarity constraint, of course, doesn't move. It's fixed. We can't make it any better. Whereas the Higgs cubic self-coupling, if you measure it precisely, it can move that bound in and start either ruling out parameter space or show a deviation from the standard model value, indicating perhaps a new Loryon. Okay, the last thing I want to talk to you a bit about is this potential effect on the electroweak phase transition. So as I mentioned, these particles, since they're strongly coupled to the Higgs, you could naturally expect that they have a significant effect on the Higgs effective potential and influence the electroweak phase transition. And this is indeed borne out. So in these plots, the blue region with a solid boundary is the unitarity bound. The orange region with the dotted boundary is any of the experimental constraints. And this green region with a dashed boundary shows the region of the parameter space in which we predict there would be a strongly first order electroweak phase transition. And you can see that in general, for these models, that region where you get a strongly first order electroweak phase transition goes right in the middle of the viable parameter space for Loryons. So the intuition is indeed borne out. These particles are strongly coupled to the Higgs. You'd expect to see this sort of effect. And indeed, if you have a new Loryon, there's a good chance it would give you a strongly first order electroweak phase transition. Okay. With that, I'll leave you with some concluding remarks. So to summarize, if you want to integrate out a particle acquiring most of its mass from the Higgs, a Loryon, and describe its effects on standard model interactions using effective field theory, you must use heft as your effective field theory. You cannot use SMEFT because it does not converge. Loryons necessarily appear at around the electroweak scale, and while there are constraints, there are sizable viable regions of the parameter space, and so it is quite possible that there could be BSM Loryons. And we can find out a lot more in the near future. Improved measurements of Higgs properties, such as with the HLLHC or other projected future colliders, could either lead to a discovery. Again, if you're being an optimist, you say, aha, we could discover new Loryons. If you're a pessimist, you say, well, these near future colliders would substantially narrow the allowed parameter space and could eventually rule Loryons out. Finally, the large coupling that Loryons have to the Higgs means that, by definition, they are natural candidates for generating a strongly first order electroweak phase transition, which is of interest in numerous contexts. So I think with that, I realize it's gotten dark and I'm a bit hard to see, so I'll turn a light on, but then I'm happy to take any questions. And thank you again for your attention and for listening to my talk.
Okay, thank you very much for the nice talk. Other questions or comments? Maybe I ask a naive question. Can you go back to the slide where you showed this criterion of the convergence of the series expansion? Yes. So here, do you first start with this L effective Lagrangian and then expand it in powers of this expansion parameter lambda b times h squared divided by mf squared?
Yes. So this is you want to integrate out our new Loryon. And you could, if you like, integrate it out to some fixed order in the Higgs doublet H, for example, but it's also possible using functional methods, which is work developed in this prior paper by my collaborators is to show that you can integrate out such a new particle to all orders in the Higgs doublet H. So
Okay. Mhm.
if you integrate it out to all orders in that field, that doesn't get you either SMEFT or heft immediately.
Mhm.
In order to have a SMEFT or a heft description, you then need an expansion in powers of the appropriate field for your EFT description. So after doing this integration to all orders, as a second step, you expand in powers of either the doublet big H or the physical Higgs boson little h.
I'm a little bit confused because so suppose that the expansion parameter violates this inequality.
Mhm.
And does it mean that the effective Lagrangian before the expansion becomes infinite?
No, generally the effective Lagrangian is still fine and you could use it, but
Okay.
because it has terms like essentially log of 1 over 1 plus x.
Uh-huh.
If you think of pulling out this term, say, and log of 1 over 1 plus x, you can Taylor expand for small x, but it has a finite radius of convergence. But the function log 1 over 1 plus x is well defined for large x as well as for small x. You just can't Taylor expand around x equals 0 and have it converge for large x.
Okay. So it means that the maybe truncation of the series at a finite order does not work.
Exactly. And this is a problem for EFT analysis, because if you're doing an EFT analysis, you want to truncate at some finite order, such as dimension 6, as is commonly done with SMEFT, and then only compute to that dimension. You can do that only if the higher dimension operators become less and less important. And if you violate this condition, then that is not the case. And if you were to try to do an analysis using SMEFT, and you were to compute, say I want to work at dimension 6, what are my dimension 8 effects? Are they small? You would find no, in fact, dimension 8 is more important than dimension 6. Dimension 10 is even more important, and so on up the line. You don't have an expansion that you can truncate to get a good, to calculate with reliable results.
Thank you.
Mhm.
Further questions?
I have one question concerning the direct searches. So in the bounds, were you also considering searches for the additional scalars or vectors directly, or are you only considering bounds from modifications of the Higgs?
No, so these direct searches are bounds from searches for the new scalars directly. It varies highly depending on the particular representation you're looking at, of course. But these are, for example, for the colored examples, you can, because you'd expect them to be produced in Loryon processes and see jets, and they contribute there. This charge singlet, for example, is, you can write a coupling between leptons, an anti-symmetric off-diagonal coupling between leptons, and you get a bound on the mass from that. And so we considered a wide variety of direct searches, aiming to get whatever the current strongest bound is. And this is discussed in great detail in the paper. So I would encourage you to go there.
Yeah.
Because we lay out explicitly which searches we used for which particles in each representation. And
okay, and but for this, the interactions you consider are the interactions you had in the beginning, because, for example, with this particle content, I could also write down a coupling between the new scalar, a vector-like quark, and a top directly.
Right, so these are all considering only standard model particles and whatever Loryons we introduce. We do impose the Z2 symmetry as said before. So
okay.
this rules out many Yukawa interactions you might wipe
I see.
down.
Yeah.
But then we allow the Z2 to be weakly broken in order to allow any charged particles we introduce to decay. And so there can be small breakings of the Z2 by things like Yukawa interactions between new scalars and standard model fermions in order to allow for decay and not have stable charged particles. But we don't introduce other new particles like vector-like quarks.
Yeah, okay. And then for the soft breaking, you consider all possibilities of decay channels into standard model particles, basically.
Yes.
I see.
Yes. Mm-hmm.
I see. And
So maybe could you go back to the slide you showed to the question by Jaehyun Park?
So which slide?
This effective potential and
For the electroweak phase transition? Or do you mean this one?
no. The analytic form for the effective.
For the effective Lagrangian?
Yeah.
Yes.
So here, I think maybe you already probably answered the question by Jaehyun, but if so, you have some. If I look at the last equation, in the last line, so I mean, so Loryon does not have to satisfy this condition, right? In general.
Right. So Loryons are the name we give to particles which get most of their mass from the Higgs, where that is fixed by this condition, which is that you're required to use heft. So Loryons by definition receive more than half of their mass from the Higgs, and you are required to use heft to analyze them. So it is the defining, this is the defining condition for Loryons. And then on the second slide, I've rewritten it in terms of, rather than in terms of the ordic coupling lambda and the explicit mass M explicit, I've rewritten that same condition in terms of.
Okay, so let me ask you in
Abstraction
different
analysis.
way. So in the previous slide,
Mhm.
so suppose this condition is not satisfied, or in any case, so your point is that the expansion in lambda over MEX square that converges in the SM-EFT and also Higgs EFT in both cases, or?
So it always convert in for a heft analysis. You don't expand in powers of the Higgs doublet.
It's
You
in
write
the
it in
physical
terms
Higgs, yeah.
Right, Higgs VEV and the Higgs boson. And so the expansion is about the physical vacuum.
Right.
And so by construction, it will converge at the physical vacuum. So heft works no matter whether you're using a Loryon or not a Loryon, you can always do heft. SMEFT expands by definition, you want to linearly realize SU2 cross U1, you expand in powers of the Higgs doublet. That's an expansion about big H equal to 0, the electroweak preserving point, and it converges at the physical vacuum only if this condition is satisfied. And so if you have a non-Loryon, a SMEFT expansion will converge. And if you have a Loryon, a SMEFT expansion will not converge. As a practical matter, if you have something that is just barely not a Loryon, like if it gets 49% of its mass squared from the Higgs, a SMEFT expansion would converge very slowly. And so it would be much better to use heft rather than SMEFT, because to get a good answer in SMEFT, you would have to truncate at high order because your expansion converges very slowly. But it does technically converge, and so you could use SMEFT if you want.
I see. Yeah, I was interrupted by something else during when you were talking about this part. So sorry. Okay, thank you.
No worries. Yes, it is. Yeah, this is the condition for a Loryon. It's because your SMEFT expansion does not converge if lambda v is too large relative to m explicit squared.
And in the later part of your slide, you listed some experiment constraint, and you mentioned the Higgs wave function renormalization. What do you exactly want to say about this one?
So any particle which is coupled to the Higgs provides a correction to the Higgs wave function renormalization, and it shifts all the Higgs couplings, and that's how you could observe it. So if precision measurements of that, such as at a future lepton collider, E plus E minus to ZH, can strongly constrain the wave function normalization, which places limits on having any new particles coupled to the Higgs. Since Loryons have to be coupled to the Higgs, this could place a significant bound on them. The current limit from Higgs wave function renormalization is not competitive with the other bounds, but in the future, it could be a significant constraint.
Okay, thank you.
I would have one more question, which is rather generic. So I was asking in the beginning, you are assuming for your starting Lagrangian that electroweak symmetry breaking is linearly realized in that. Now, I'm particularly interested in composite Higgs models. So if I would want to include those, naively, I would think I can take your Lagrangian as a starting point and basically add higher order operators to this Lagrangian already, which would give me more free parameters, but I could follow the same sort of logic and construction in order to include those. Is this correct, or do you see any points which do not work if you realize the electroweak symmetry breaking non-linearly?
So I think that you could do such a thing. I think so. I'll preface this by saying I don't know too much about composite Higgs models, but the main one, or at least a significant reason for Loryons being marked out as a class of particles is because of this interaction with SMEFT, which linearly realizes SU2 cross U1, saying that if you're doing an effective field theory analysis of the standard model, if you have a Loryon, you cannot do that analysis using SMEFT. You must do it using hep. And so if you, for some other reason, already cannot use SMEFT to do your analysis because you're not realizing SU2 cross U1, then this Loryon's distinction becomes much less important because you already can't use SMEFT as your effective field theory of choice. So all these particles we've introduced, you could take the Lagrangian that I've presented as a starting point and add additional higher order terms, as you say. But I'm not sure the Loryon's distinction would be particularly relevant in that case if you're not wondering about whether or not you can describe the theory using SMEFT as an effective field theory. Otherwise, you just have particles which are strongly coupled to the Higgs, which may or may not be. How relevant they are would depend on what else you're doing.
Yeah, no, I mean, the models I'm interested in realize the Higgs as a pseudo Goldstone boson multiplet, which respects custodial symmetry at leading order. So in that sense, and the corrections just by not having being immediately ruled out by Higgs precision data is also that you have, in a way, a controlling parameter which suppresses the deviations or the breaking to the custodial symmetry. but maybe I am misunderstanding something. The fact that you have that you can apply SMEFT, why is this so important? Because you could do the analysis in heft as well, and the constraints or the plots you were showing on the parameter space, I mean, those are in the end physical constraints, so it does not depend on whether you use SMEFT or heft, right?
Right. So generally the distinction SMEFT is easier to work with because it has more restrictive symmetries. It has more symmetries, so you have fewer operators. It is easier to work with, and it has been, for that reason, when people have done EFT analyses, they have chosen to do them in SMEFT rather than in heft. As you said, you could just do your analysis using heft in the first place, and then you wouldn't have to worry. And that is entirely true, but that is not what people have done. And so part of the point in discussing Loryons is to say, hey, you shouldn't just default to using SMEFT because you might be missing something.
Mm-hmm.
The constraints I showed, as you said, those generally come from the kappa framework of saying, oh, here's Higgs to 2 photons and just stick it, or other couplings, and sticking in a kappa parameter, which can scale to tell you how you deviate from the standard model. That is, I mean, the Lagrangian you get when you put in kappa parameters, if the kappas aren't equal to 1, is not gauge invariant. It's not a proper quantum field theory. And so you would rather do a full effective field theory analysis as opposed to just this kappa parameter analysis. And that will be particularly important if you're seeing deviations and you want to correlate your deviations and see which models they're consistent with. You need the whole effective field theory framework to write down a consistent theory.
I see. So you're saying the interpretation of the bounds would be much more complicated in that case, because you cannot just take over bounds from the literature on, for example, the kappa framework.
Exactly. You'll want to use an effective field theory framework, and SMEFT is easier to work with than heft, but you can miss things by using SMEFT, and it won't always work.
Thanks.
Yes.
Not a physics question, but
Okay.
what is the English interpretation of Loryon? Why did you name it that way?
Right. So that is, so the name quarks originally Murray-Gell-Mann got the name for quarks from Finnegan's Wake. And Loryons comes from the same place. We decided that's a good idea, just pull names from Finnegan's Wake. So it was in fact Nathaniel who pulled down his copy of Finnegan's Wake, and he just paged through it, and Loryons appears in there, and that sounded like a particle name to us. And so we call them Loryons.
Ah, okay.
That's it. It's just,
Ends
yeah.
in on,
sorry?
because it ends with the ON.
Right, it ends with ON, so it sounds like fermion or boson or the like. It could be a particle, and other than that, it's a word that James Druce came up with in Finnegan's Wake, and the same as quark, and so there you go.
Further questions or comments? Okay, if not, let us thank Ian again. Thank you.
Thank you.
Yeah.
Bye-bye.
And thank you again to everyone for listening and for the questions.
Mm.